Swayam Prabha. Digital India. Educated India.
Okay, we'll continue with the discussion on classification of polymers. If you recollect that we've been looking at classification based on several factors. You could think about origin of this material. So we say okay, natural versus synthetic. Then there are classification based on how we process them, thermoplastic, thermoset, and and so on so. And then also based on the chemical families. We are talking about what are the functional groups. Depending upon them, you can classify them as in polyolefins, right, and polystyrenes and acetal, nylon, etc., right. So in that line of thinking, there is one more way in which we can classify the plastics or polymers, that is based on the topology or the molecular architecture, or we say the conformation, okay, how the spatial distribution of atoms look in a given polymer. Okay. So if you see all these cartoons here, kind of characterize different kinds of polymer that you will encounter. There are polymers that are linear. Sometimes the linear molecule can have some side groups. Then you can have some ring-like structure in between, or you can have ring-like polymer attached. You can have a backbone and then side chains, branches, or you can have actually cross-linking. Then you can have entangled branched polymers, or you can have cross-linking in a very disordered fashion. You could actually have mixtures of cross-linked polymer together, and then you can have very complicated structure, something like a chromosome where you have a kind of a backbone, and then there are many branched loops. There are proteins that kind of do some biological functions. So, broadly speaking, there are polymers of all kinds of topology. Okay, so that's the context. So now if I go to each one of them separately, so when we say linear polymers, in this case we think about adding monomers along a chain, okay, and a growing chain. So we say them as a straight chain or a linear chain polymers. Okay, very simple example is let's say if you think about polyethylene. So polyethylene is made by combining vinyl group, which is CH2 group, in an additive way. So you will see that the polymer takes this kind of a topology. They are not necessarily a straight chain, but it has this kind of zigzag kind of arrangement. That is because of this CC bond having a particular angle. Right, it has to have this 109.5 degrees of angle between the bonds, right. So you will have this kind of a zigzag kind of nature. And one more thing you will see that is characteristic of a linear polymer is that about the CC bond, the bonds can rotate. Each bond can actually rotate above the axis. What that means is when you have a chain, linear chain like a polyethylene molecule, it can undergo a lot of different rotation, twisting, bending. So you will see like a very flexible chain, okay, when you put this polymer in a solution. Okay. So that's because of that you see that because of CC bond rotation in a linear polymer chain, there is a possibility of bending. It can coil up, it can twist, and it can entangle with other chains and so on. Okay. So those are some of the important characteristics of linear polymers or straight chain polymers. An example is this polyethylene, as I mentioned already. So within linear polymer, there is also something called stereochemistry or stereoisomers. What it means is that even if you have a straight chain, some of the side atoms can take different orientations or different conformations. Okay. So this is called a tacticity of a polymer or stereochemistry of a polymer, right. So here we have given an example of polystyrene. So what you see here, all of them are polystyrene, but in this two-dimensional representation, you can see the way that styrene side group is arranged. In this first example, all the styrene groups are in one side, all the hydrogens are on the other side, and there is a hydrogen between each of the aromatic group. Okay. This we call them as an isotactic polystyrene. Okay. Now you can change the chemistry of polymerization, okay, and you can actually change the order in which this styrene monomer is distributed. Here you can see that there is an alternative arrangement of styrene monomer. It is in the bottom first and then goes up, and the next repeating group it comes down, in the next repeating group it goes up, and then it alternates. This is called syndiotactic arrangement. Okay. So in a chemical formula they are all the same. You will write polystyrene polymer chemically the same, but if you look at the distribution of side groups atoms, you see there is a difference, and this difference manifests in the physical properties and chemical properties too, in the way that they can pack, the crystallinity, the temperature resistance, and many other mechanical electrical properties can be very much dependent on the isomer. Then there is something called atactic. Atactic basically means that there is no particular order, okay. So they are basically randomly placed on the back chain, okay. So depending upon how you synthesize the polystyrene molecule, you can actually have isotactic, syndiotactic, or atactic, okay. So this is one of the characteristic of a linear polymer. Whenever you have a linear polymer, you could ask, is it a syndiotactic, is it isotactic, or is it atactic? They all have different properties. In fact, the biodegradability of a polymer lot more depends on stereoisomers. Some form of them are actually easy to degrade, while others may not be. So when we think about biopolymers or biodegradable polymers, we also have to keep in mind it is just not only the chemical formula, but also the topology, the conformation of side groups also very important. Okay. So there are studies where people have studied about the degradability of different stereoisomers. The one that forms a very nicely packed crystalline structure that happens when you have a isotactic or syndiotactic, they are very hard to degrade. Whereas when you have this atactic, they form mostly an amorphous structure and they are easy to degrade. So if you are thinking about a biodegradable polymer, you have to think about amorphous nature, and how do you prefer amorphous. So I was saying that so we got this linear polymer, and the linear polymer can also have this different stereoisomers, and they affect its crystallinity, packing, density, mechanical properties, biodegradability, and etc. Right? And we say that stereoisomers are nothing but these are compound having same chemical formula, but with a different orientation or placement or topology of the side groups. That's the context, right? Now there are something called branched polymers. So branched polymers are basically you have a linear chain, but along the backbone you can actually induce side chains, and introducing side chain is one way in which you can change the properties of the polymer. So I have given some examples here. If you think about this polymer, this is basically a polyethylene, but then in the polyethylene we have also added some small side groups, okay, small branches. And for example, if you look at the commercially available LDPE, that is low density polyethylene, typically for every 1000 carbon they introduce something about 40 methyl groups along the chain. So you see, so whatever I have shown here as a schematically, here we have shown as a chain. So this is a polyethylene chain, CH2, right? And then you see that once in a while we introduce a small side chain which is methyl group. Sometimes we also introduce a long side branch which contains CH2, groups. So this is a characteristic of a low density polyethylene. Okay, the low density polyethylene, which is very low density, very easy to, it's very flexible material, is actually manufactured by taking a linear polyethylene chain and then introducing few side groups. These side groups could be shorter side groups or could be longer side groups. The shorter ones are methyl groups, the longer ones are ethyl groups. Okay, and this kind of tells you the density. For every 1000 you have 40 small groups, 1 to 5 long chain groups. That's the characteristic of a low density polyethylene. And then we have another version called high density polyethylene. In the high density polyethylene, we basically introduce for every 1000 carbon there is about 3 to 5 methyl groups, and there is no long chain groups in HDPE. Okay, and because of this difference, the HDPE has a higher density because it can pack very well, and it has more rigidity, or otherwise having a less flexibility than LDPE. So what we are saying is, within the linear polymer chain, There are other things like stereochemistry, stereoisomer. Then we can also induce the small side groups. All of them is done to change the way that the polymer pack form crystalline or amorphous material. Okay. So, commercially available LDPE, HDPE, they all mean that in the backbone chain, there is an introduction of side groups, and this actually makes a huge difference in the way the polymers pack. Now, if you extend the side groups into a long chain, then you have something called grafted polymer. So, in the grafted polymer, what we have is we have this main chain, right? You have this main chain, and then along the side you can actually add another polymer and grow another polymer on the backbone as a side groups or branches. So, the difference between the previous one and this one is that in the previous case the side groups are shorter elements. In the grafted polymer, each side chain is a polymer of a different kind. Okay. So, I have given one example here. So, we have polystyrene polymer, and then once in a while we also attach on the side group a polybutadiene. Okay. So, polybutadiene is a rubber. Polystyrene is a very brittle polymer. Okay. When you add a rubbery material on the side chain, you can actually introduce flexibility to polystyrene. Okay. And it can actually be more tougher. Okay. So, an example of this is a high impact polystyrene. Polystyrene naturally is very strong, but it is also very brittle, it is easy to break. So, to include toughness, you basically add rubber, not physically added, but a polybutadiene, which is another rubber, is actually grafted meaning added as a side group to the main chain polystyrene. Okay. So, that is what we mean by polystyrene blended with the polybutadiene is a grafted polymer, which has this kind of a cartoon that we show, but chemically this is what it means. Okay. So, this is done by a controlled addition of a second polymer as a side branch onto the main chain, right. Any question at this point? Then we have a set of cross-linking. We already mentioned about cross-linking, which means that there is a chemical bond between the side chains that holds the molecules together, and the cross-linking bonds are as tough, as strong as the main backbone chain itself, right. And many of the thermoset are made up of cross-linked polymers. So, now when we think about cross-linking, we also say something called cross-linking density. Cross-linking density basically means how many cross-linking network points are there. If you have a very highly cross-linked into a network, you will form a very rigid structure. When you have very few cross-linking networks, you would have a more flexible materials, right. So, most of the thermosets and elastomers, these are all cross-linking based. So, here I have given an example where here we have two polymer chain, they are cross-linked through a cross-linking agent. So, here we have a set of flexible network and there is a few cross-linking point. This is a cross-linking point, this one is a cross-linking point. So, typically you will see this kind of a thing in a vulcanized rubber, okay. And this is basically this is an example of cross-linked polyethylene, right. So, as I said that this is very common in thermosets or elastomers, and thermoset or curing, we also call this curing, setting, vulcanization, they all basically refers to the same as cross-linking, okay. So, cross-linking is another method by which you can change how flexible the polymer is or how rigid the polymer is, that you control by adding a cross-linking agent, cross-linking it. You can also change the number of cross-linking point, therefore, you have a control on to what extent you cross-link this. There are other newer set of polymers where we blend cross-linked polymers. When you have when you have two or more set of cross-linked polymers, you can actually make an interpenetrated network. So, what you see here is there is a continuous line which represents a cross-linked polymer network. There is also on the background we have another one which is shown as a dash line, okay. There is a polymer network, cross-linked polymer network shown in a dash line, and they both are actually interpenetrating, okay. So the reason to have such a interpenetrating network is to have a combination or a synergetic property enhancement. So there are two kinds of polymer here, right? So each one will bring this own mechanical properties. So the blend will have a combination of those. Okay, there are not very many such blend because typically they phase separate, they don't mix very well, and these are a new set of polymers that are finding a lot of applications, emerging applications. Then there are polymers which are actually composed of only rings, aromatic rings. Okay, so you can see it has this ladder like structure, so it's also called as a ladder polymer, but basically made up of connecting aromatic rings along this line, right? So okay, so far it's all about topology and how we control how we classify polymers. Now I want to switch to another topic, which is additives and fillers. Any plastic product that we see, right, they are never pure polymers. Okay, there is always something added, and these added components are called fillers or additives. In the next slide I will show you why we add those fillers and additives, but in terms of definition, fillers and additives are not the same. There is a subtle difference between them. Okay, we call them as something filler if when added along with the polymer, we are able to visually see this added material as a distinct face or a visually distinct object. Okay, for example, I have given an example. Let's say you have a glass fiber added to a polymer. The glass fiber is physically different thing from the rest of the polymer matrix. Okay, through microscopy you can see them. They are two different objects. Okay, it's visually different. Similarly, when you add a coloring agent, the polymer itself takes this color of the additive. So these are visually differentiating materials, and we call such material as as a filler. The additive is opposite. When you add an additive, you can't really distinguish them as a separate phase. They are integrated into the polymer matrix itself. You will not visually see them as a secondary phase. Examples are something called plasticizer that are added to plastics to make them more flexible. Example would be adding oil or glycerol or any sorbitol. These are some of the chemicals that are added to increase flexibility, to add flexibility to the material. But when you do microscopy, you will not be able to see them. Okay, they are more like a small solvents that are taken into the polymer matrix. So these are very subtle difference between additives and fillers, right? Now this kind of lists all the reasons why we would need fillers and additives. Okay, there are different reasons. Many times the polymer as such may not have adequate strength, adequate mechanical property that you need, right? So what they do is they add an additive to enhance the Young modulus or elastic modulus of the polymer material. Sometimes you want to increase the strength, toughness, hardness, depending upon the application in kind. Okay, and many times we actually want to add a filler because the original polymer may be quite expensive. So instead of using 100%, maybe you can have 80% of the polymer, 20% of low cost additives, so that the net mass is maintained, but then the polymer fraction is less, so you can cut down cost a little bit. So it can be just a reducing cost with no big functional role of the additives. Many times we also add additives or fillers to actually prevent oxidative degradation. Okay, so when we think about a plastic product, you want the user to use as long as possible. When you sell a plastic product, we don't sell thinking that it should degrade after some time, in the current setting at least. So oxidation is a very common phenomena by which polymers will degrade. Okay, if you have ever bought this silicon case for your mobile phone, the transparent glassy, right, and then after some time you will see it become very yellowish. Okay, so that's because of oxidation. Okay, and you see that after some time you don't feel like having it and you'll throw it and buy a new one, right? So sometimes we add something to prevent that kind of an oxidation. Okay, you buy a product that is white, and then with the oxidation, if it turns yellow, you don't feel like having it, right? So there is a additive that is added to prevent such an oxidation during use as well as while preparing this polymer. And then commonly we add colors, because that's one of the advantage of using polymer products, that you can add any color you want, you can make them very shiny and have a variety of colors. Okay, adding adding fillers to increase flame resistance is a very important thing. Polymers like PVC, like polyvinyl chloride or Teflon, we are actually I'll probably give that example later. You want to actually make sure the plastic is not shouldn't be actually inflammable. Okay, so you want to add something to reduce that property. By nature, all polymers are flammable. It's easy to burn. Okay, and how do you resist prevent catching fire is also important. So they add something called flame retardants. And then to add flexibility, I already mentioned. And sometimes you want to enhance or decrease electrical conductivity, right? And then to provide so it's a new thing that add something so that it can degrade when littered after use. Okay, so to provide some sort of biodegradability, you add some compounds. And then if you want to control the polymers in making crystalline polymer, you can also add something that will act as a nucleating agent to enhance the rate of formation of nuclei, right? And sometimes we have polymers that are foamy. For example, expanded polystyrene, polyurethane, these are foams, and you add a component so that during processing it will release some gases to give that foamy structure. Okay, so these are all typically used additives and fillers. What you actually will need depend on what application that you are looking for. Okay, so let's go to each one of them separately and then give some context with some examples also. So the antioxidants and stabilizer, as I mentioned, is a chemical additive that is added to prevent degradation due to oxidation or UV irradiation during processing or after use. Carbon black is very good example of this UV resistance, because carbon black absorbs UV light so that the polymer does not get affected. Okay, and it's common to see carbon black added to low density polyethylene or polypropylene to an extent of about 0.2% or so. Okay, so then we have something called this plasticizer. The plasticizer added to give flexibility to the material. For example, polylactic acid, right, PLA, that we think biodegradable, is a very brittle. You cannot draw film, so you need to add some sort of a plasticizer or other polymer which are more flexible to increase plasticity. So plasticizer example can be glycerol, sorbitol, oils, vegetable oils, and so on. So then we have something called preservatives. So preservatives are if you make a polymer that are biodegradable based, like for example if you want to make a starch based polymer, you will see immediately after some time fungus will grow, a microorganism will grow. Okay, so sometimes you want to add an antimicrobial agent to prevent growth of microorganisms. Sometimes you want to have rodent resistant or insecticides. So typically you add antimicrobials, fungicides, rodenticides to avoid these kind of to preserve the intactness of the polymer. And as I said, flame retardant. So flame retardant, the reason to use a flame retardant is to increase the ignition temperature. So ignition temperature means the temperature at which it will catch fire. By adding a flame retardant, you can increase that, or in other words, you can actually have a agent that will scavenge the free radicals. Okay, mostly halogens are used for this application. Chlorine, iodine, fluorine, bromine, these are typical compounds that are used as a flame retardant. So examples are like PVC, PTFE, they contain large amount of this halogenated compounds. Another example, this alumina trihydrate powder, it can be added as a filler, and when it catches fire, it actually releases large amount of water, H2O. Okay, so that can be also a strategy to prevent flame. Okay, so in fact, there's a huge research possibility in coming up with something eco-friendly flame resistant retardants, because the halogens are not very good, because once you use them, you can't recycle it. If you try to recycle it, you basically release a lot of halogenated compound in the air, and that's going to be highly polluting. So there is a need for developing fire retardants that are not halogen based, but still it should function as a flame retardant. So there is a huge requirement there. And then going to fillers. So fillers are typically used for reinforcement to increase this toughness, strength, hardness, etc. So typically carbon black is added, silica is added in rubber tires and rubbery materials. In other textiles and other apparels, they also add glass fiber, Kevlar, graphite, boron in plastic materials. These are typical examples of various fillers. Then we have pigments. Pigments are nothing but coloring agents. Depending upon what color you want to add, you can add different coloring agents too, right? So here is an example. There is something called this Rubber World Blue Book. Okay, it's basically like a cookbook. It's a recipe book that contains plastic formulations. Okay, that if you want a particular compound to be made, what are the recipe? Okay, you basically buy these resins and various things and add and mix, and that's how you mold it. Okay, so if you look at this, it is basically a rubber material. Okay, let's say it could be a tire, let's say. Okay, you can see how many compounds it goes. It's just not only rubber. There are so many additives, so many things are added. So look at the first one is a neoprene TW 100. These are two different grades of neoprene rubber. Okay, so they take 60:40 ratio. It's a blend of two neoprene grade polymers. For every 100 parts, let's say by weight, then you add various other things. Okay, so here they add these two neoprene polymer because they want to get some sort of average property of both of these polymers. Okay, then they add something called this maglite, which is magnesium oxide, as a part of curing package. Then carbon black N762. So this is a commercial index. Okay, so you should be able to buy with this index. You should be able to buy carbon black. Okay, that would have a particular particle size, particular properties, right? And you add that as a reinforcement to give toughness to the rubber. Then you add clay. Clay is added not for any functional role, but just to reduce cost. You want to give adequate weight for the rubber. That weight cannot be only by polymer alone, rubber alone, but you add a clay because clay is very cheap, right, to give overall height, strength. So you can see that for every 100 grams of the polymer, you add 45 grams of clay. Okay, so that's a lot of clay. Then they add something called stearic acid, which acts as a lubricant or a plasticizer or processing aid, which allows them to mix and flow and Then they add this something called zinc oxide. This is also part of curing, and there is something called octamine as an antioxidant because you don't want the rubber to oxidize when you process them at high temperature. Then there is something called, I don't know what this is. This is called Wingstay 100. I don't know what it is. It is saying that it is for ozone resistance. Again, maybe to reduce oxidative degradation. Then there is something called sunproof regular. I don't know what it is. It works with the Wingstay, that is the ozone resistance. So they have figured out some way in which they can actually do this ozone resistance. Then something called Kenflux a chemical that is used for a processing aid, and then Sunflux 79T as a plasticizer. So you can see that it is not a one single compound, right? It's basically a mixture of many things. This is just one representative example. If you look at some other application, let's say you want to make a rubber for your shoe or something, it would have a different composition. Okay, these are all like I said, this is a reference book which you can refer to find what is the typical composition of various material they do. Okay, so one thing is clear, that it is just not only about the polymer. So many things are added. This is what makes the degradability a very big issue, right? So you see that in this, suppose if you take this particular tire and I want to recycle it, it is just not only the rubber. I have to separate the clay, I have to separate all these chemicals that goes on. Many times we don't even know as a user what is the chemical nature of this, which are safer, which are not safer, we don't know. Okay, So that's what the fact that we're so used to make a mixture of many things to make a functional plastic puts a huge complexity issue on recycling it. If you want to think about recycling it, how are you going to separate all these compounds, right? So you have to think about how to come up with a formulation that after use it is fairly easy to recycle, yet provide the same kind of functional properties. So that's really a challenge, right? Okay, so I think that's all I have. Yeah, so that's all I had to say about classification. The whole idea is to give a very broad overview. It's a very monologue. I know that's very monologue, that I'm just telling a lot of information. But the context is that when we move further, you have to keep all these things in your mind, that any plastic product is not a single product of a polymer. Right? It's a combination of inorganics, halogens for fire retardancy, and antimicrobials. There's a whole lot of things. Okay, so this basically puts a huge complexity pressure on how to do this recycling. Okay, if you have only a simple, even if you think about PET, for example, right, PET, even then it's not simply a PET. That would also have many of these. It would have had a minute quantities of oxidative, antioxidants. It would have some amount of, flame retardants. So you have to look at all this. Any plastic product, you will see all these things. Okay, so recycling is a big issue because of this reason. Okay, so that's something I want to add. Any thoughts? Anything else you want to add to these points? So if you have a mobile phone, can you go back and check the blue book? It is not available for free, but see from your try to find some composition of a rubber material through this Rubber World blue book. Maybe you can spend few time and find out some typical recipe.